The big idea for today is factor. And it's important to think about what factoring means in general. Factoring in general is just reducing or breaking down something into two different products or maybe three or more, depending on what we have. So when I look at the idea of factoring here, I threw this one out here to try to trick you guys a little bit. And notice how it's not written in really nice format. We like to write it in standard form, so that's the first thing I would do, is just rewrite it so it's in the correct order. And that just makes things look a little more friendly. And now all of a sudden we're looking right at, what did we do last unit? We did the box with the circle. So I'm going to come over here. Plug those numbers in and then multiply the corners. So when I multiply the corners, I end up with negative 40x squared. And I'm thinking, what are my factors of negative 40 that add up to give me positive 3? So right away I'm thinking, well, 4 and 10, no, that doesn't work. 2 and 20. I'm going to recalibrate this quick. It's been off. So factors that give me 40 that are 3 units apart are 5 and 8. However, one of them has to be negative, and I want more negatives when I add them together. So the negative goes to the 8. We'll put a 5x and a minus 8. So that's filling in the box, and now we take the idea of actually factoring, and that's pulling out the common factors. So we go straight across, and I see I have a 2x in common across the top. Across the bottom, we've got a factor of positive 5. Vertically on the left, we've got a factor of x. And then vertically on the right, we've got a factor of negative 4. Now we're not done there, right? That's just the method that we're going to use to get the factors. The actual factors are when you write them as a product, because that's what factoring is. It's a list of all the items that multiply together to give you the original expression. And then I threw the second one out there just because this one comes up a lot, and I know we didn't cover it a ton in Chapter 4. So I just want to make sure you guys are really familiar with it. If you got stuck, that's a good thing, because you thought about it, you tried some things. Here's what you could do with this problem. You have two terms. Really, the big idea today is we're looking, what does each term have in common? Shoot. Oh no. So if you really wanted to, when there's only two terms, put a box around each item and think, what common factor do both of them share? Well, I know 3 divides into each one of them, but that's not the greatest common factor. Right? A 3 plus an x. So that's what we're going to pull out, is a 3x. Then we're thinking, well, what's left over? What's left over is an x and a minus 9. And then again, we're not done. Our answer has to be written as the product of those factors. Okay? I'll actually focus up here. And then the last problem, it looks intimidating, right? And you could make this problem really challenging if you do the wrong step to start. But notice, it just says solve. Well, what if I told you to solve the first two? You would factor and set each parenthesis equal to 0. Well, this last example, it's already factored for us. So all we have to do is take each grouping and set it equal to its own 0. Now there's two options with this one. If you want, this is one of those special patterns. You could factor this as x minus 9 and x plus 9, and then set each of those equal to 0. Or, because there's just a single term here, you could just solve this by moving the 81 over, and that's the route I'll do. And then I have to take the x squared plus 16 and set that equal to 0. Notice, this one, x squared plus 16, does not factor, because there aren't any factors of positive 16 that add up to give me 0. So that's just, the more you guys get used to this, the more you're going to see those patterns develop. So really, I just have three equations that I have to solve. First one, divide by 3, which tells me one of the answers is x equals 0. The red one, I have to isolate the x squared, so I have to add 81 over to the one side. And then we're going to take the square root. But, as we talked about last unit, when I take the square root, the square root of 81 is 9, but it's the absolute value of that, which really means you can have two answers. You can have a positive 9 or a negative 9. So we usually just put plus minus 9, and that represents our two answers. And then the last one, you might already know what is going to happen with this just by looking at it. If I move the 16 over, I get a negative 16. I isolated the square. Then I have to take the square root of both sides. And now we're going back to, like, maybe this is a little side work for us. But anytime I take the square root of a negative, we can call that square root of negative 1, which is 5. Right? And then we know that the square root of 16 is 4. And yes, I could put the absolute value bars here, and I probably should, because I get 4i, but then we know that that's a positive and a negative 4i. So these are things I'll say from now on we expect you guys to do pretty consistently. I'm not saying they're easy, but you can hopefully feel confident, and over time you're going to look at this and be like, oh, I got this one, no problem. Now, how does this all tie into what we're doing today? Well, we're studying polynomials. Technically, this is a polynomial. This is a polynomial. This has 3 terms, so it's a trinomial with a degree 2, which is a quadratic. This is a quadratic as well, because it's a degree 2, but it has 2 terms, so it's a binomial. And if I was to expand this out and multiply it, I would have an x times an x squared times an x squared, which would give me an x to the 5th power. So eventually this would be a 5th degree polynomial. But notice, it has solutions. It's got 1 solution here, 2 solutions here, so it's got 3 real solutions and 2 imaginary solutions. So we can still take that knowledge that we had from chapter 4, finding solutions, and if something is in factored form, all we do is set each parenthesis equal to 0. And then we solve. So hopefully you guys can say, okay, cool. Once it's factored, I can solve using any of the method that we just talked about. So the only new part today is how do we factor when things don't look like the warm-up in problem 1. Okay. And that's our goal. I do want to mention this really quick. I put this up here so I didn't forget about it. I started grading your tests last night, and they took a little longer than I thought. I graded for almost 2 hours, and I got through 3/4 of our class. And I still have my 6-hour class to do. So it's a longer thing. But here's the thing. Some of you may have seen your results already. And you might have noticed that the scoring doesn't match what's written on the test itself. And that's kind of an error on our part. The reason why that is in years past, when we've used an exam like this, we were able to enter the grade in our campus gradebook, and we just put a multiplier of 2, meaning it's out of 25 points. If you add up all the points on this test, all the points here are worth 25 points. But every test we've had this year is worth 50 points, and we wanted the same thing here, and I can't just go ahead and double the score. So what I ended up doing was, let's say, because this happened with a handful of people. Let's say you got task 3 wrong, or you did something wrong. A lot of the errors are students are not showing their work to use the quadratic formula. That's exactly what the directions said. So if you didn't do that, that was worth 5 points. Well, you could still get the answers from the way it was written in task 1 or task 2. So if you did that, you got some points off. But really, think of this, instead of 5 points, think of it as worth 10 points. So if I say minus 6 points, which I did on a couple people, I said task 3 minus 6 points. Some people are getting confused because it says it's only worth 5 points. So just know that really every single one of these point values here is doubled. And that's how it's going in. So that's an error on our part. We totally didn't think of it, and the reason why that happened is because of the way Schoology is synced to our gradebook. All right, so then once the test is fully graded, once everybody's done, you'll be able to open it up, and I have comments as to why I scored. So you'll need to go to Schoology, read the comments, and you can see, why did you get 6 points off for task 3? Or what I noticed down here for task 5 is, when we say find the x-intercepts, we're talking specifically, like, what are the numbers? Some students were just going like this and saying, those were my x-intercepts. I can't tell from your graph what that means, so you need to be very specific, and we modeled that in detail. Same thing with axis of symmetry, vertex and y-intercepts. I should know the numbers here, and then I should be able to see that location on the graph. If you just told me that this was your vertex, maybe let's put it like right here. I don't know where that is, right? I don't know if it's meant to be a negative 0.25 or a negative 0.5, down 6. So I made those comments when I was grading it, but I just wanted you guys to be aware, and I wish I would have told you guys sooner. So some of you saw your score last night and it was like, what happened? How did I get 6 points when it's only worth 5? Or how did I get 6 points off? So hopefully that's clear. If not, feel free to email me or talk to me about it. And again, I didn't finish everybody, so I'm going to be working on that over the next couple days. All right, quote for today. You measure the size of the accomplishment by the obstacles you have overcome to reach your goals. It's all about the struggles and challenges, I think. So here's what we got. We want to take pretty good notes here. Historically, this is one of the more challenging subjects for this chapter. And I just want to tell you up front so you can give me really strong focus in class today, as well as when you're doing the homework. These factoring methods do appear for a lot of the units moving forward. So it's not just we're going to learn it for a day and never use it again. Okay. Now, one of the nice things about factoring is, well, what is factoring? It's to take a polynomial and rewrite it as a product of linear or quadratic factors. So like x times 2, or x plus 2 times x plus 3 times x. That's factoring, right? There are 4 methods we're going to learn today, and that's going to sound like a lot. However, we've already done the first 2 methods. Method 1, you always want to do. You want to check to see, can you make your life easier by taking out a common factor? Sometimes they call it a common monomial term. Okay, and I'll model that as we go through. Remember, when you think of the word factor, it's really undoing the distributive property. That's what it's all about. Method 2 is to try the area model, the box with the circle in it. Right? So the thing I want you to know is we already learned these two methods. Now we might apply them in a different context, but I think you're going to feel comfortable with the first two methods. So with that being said, the only new methods are something we call special patterns, which we hinted at a little bit, and something called grouping. I say mostly new because we've covered some special patterns the other day. But again, the nice thing is if you don't recognize the special pattern, you can still rely on method number 2 for most of it. The cube one is the one that you're really going to have to focus on today. Squares, I'm not too concerned about with pattern. And right now, this probably means nothing to you. But it will. So as you finish writing this down, just a quick reminder of how I like to think about math. And it actually wasn't until college until I really connected with this. I didn't really think of it when I was in high school. If you think of math as like a separate skill or memorizing a formula and just doing one thing at a time and then moving on to something brand new, it gets really hard. There's a lot to go on. But what is math? Math is built upon the skills that you've already learned. And that's what makes it challenging as well, because if you haven't mastered those skills, it seems like everything is more and more challenging. So what I mean by that is we should be really comfortable with method 1 and method 2. If not, you will become comfortable with those. And that means the only new parts today is method 3 and 4. So if you can think of how things are connected, it's not learning new material, it's just building off of old. And we call that conceptual thinking. Think about the big picture. So let's look at a couple examples. This is method 1 and 2 combined together. And you'll notice it looks kind of similar to what we've seen. The only difference is I've got some higher exponents now. But I'll teach you how to deal with those, and then you'll see how one extra step can help you realize that this is a similar problem that we've already done. And we'll do them one by one here, so some of them require a little more space. But let's look at A together here. One of the things that I like to strongly encourage right away is recognizing the numbers. If I have two terms, 16 and 81, what kind of numbers are those? Perfect squares, right? Perfect squares. That's a really big hint for us. Now, you don't have to use the box method here, but because they're perfect squares, and because the subtraction, if it was addition, we wouldn't be able to use this, because the middle term technically added up to 0. But let's just kind of take a guess here. And what do you think? Oops. Look at that. See how I almost made a mistake? I put the squared there instead of the 4, because I'm used to what we did in chapter 4. But that is actually a 4. However, we're going to take the same thinking as if it was a square. How do you think I got 16? What numbers would go here and here, do you think? 4 and 4, right? So, let me erase those lines. That's kind of messy. So 4 and 4, how do you think we'll get the x squared, or x to the fourth part?
X.
Here, right? So if that's x squared and x squared, that makes this first box complete. Well, how do you think I get 81? Negative 81.
9.
Negative 9 and positive 9. So now, we don't really care about what the other two boxes are, but notice what would go here, a negative 36x squared and a positive 6x squared. Well, what do those two add up to be? 0 x squared, which is, technically, you could throw a 0x squared. So that's just one case where it's a special pattern, but we were able to factor it. Now, here's the part that you might not love. You always need to ask yourself, are you done? Can you go any further? And here's a hint. If there's a plus, you're done. This part cannot be broken down any further because of the positive 9. But don't I have that same situation we just had? 16 and 81 with the negative here were perfect squares. Well, 4 and 9, those are also perfect squares. So do we have to set up the box for this? How do you think we got this 4x squared? 2x, so I'm going to write 2x times 2x. And then how do you think we got the negative 9?
3 and negative 2.
Positive 3, negative. Now, let's do this one down. We'll do this one over here. We're not done, right? Because that part was from here, so I have to include the part that cannot be broken down as part of my final answer. And this is what we call completely factored. We broke it down as far as it can go. And the reason why I can't do, just another quick refresher, 4x squared plus 9, there aren't any factors of positive 9 that add up to give me 0. So it has to be a negative, and that's part of those patterns. Okay. Now, we're not going to do this, but what if I told you to solve? What would you do next? Set them equal to 0, right? You would take this parenthesis here, this one here, and this one here, and you would set each equal to its own 0, just like we did in this warm-up example. So, we're not going to do that for a lot of these because we already did a lot of work, right? You would take up pages and pages. I just want you to know that there are times they're going to ask you to solve. So once it's completely factored, you set it equal to 0 and just solve each one. All right, let's look at this one because this looks kind of intimidating too. Method 1 that we had said pull out a common factor. Well, let's look at these three terms. What is the largest common factor that goes into all three of these? 2. Anything else? P squared. 2p squared. See how everyone has a 2 and everyone has at least a p squared. So what we're going to do first is we're going to factor out a common term, which is 2p squared. Now that doesn't go away. It's still part of the problem. And then what's left over, if I take a 2p squared away from p to the 8th, I would get a p to the 6th left over. And then if I get a 2p to the 5th, a 10p to the 5th, if I take a 2p squared away from that, I would have a 5p to the 3rd. And then the last one, if I take a 2p away from 12p squared, we get just 6. Now, one of the things I like to do in my head is just, if you were to redistribute this, did you get back where you started? That's how you can check to make sure that everything worked out. Now, that red 2p squared is going to be part of my answer. My next goal is to factor what's left over. And this looks kind of weird too, doesn't it? we've got a 6. But I have exactly half of that exponent in the middle, which means, what if I try the box method again? So let's try p to the 6, 5p to the 3rd plus 6. I would definitely write this down because tomorrow you're going to have a quiz. And there might have to be not tomorrow, Friday, sorry. You'll be able to use your notes on that quiz. So these are perfect examples for you to have as references. So what do? We multiply the corners. And then I want to think of what type of factors multiply together to give me 6, but add up to give me 5p to the 3rd. And the hint is it's going to be a p to the 3rd and a p to the 3rd. So what numbers are we looking for? 2 and 3, right? 2 times 3 is 6, but 2 plus 3 is 5. So I'll go 5. I'll go 2p to the 3rd. And 3p to the 3rd. And then it's the same work we just did. It's just doing the box method. The numbers are a little different, but we go across the top vertically, horizontally. What's the common factor between p to the 6th and p to the 3rd?
P to the 3rd.
P to the 3rd, right? The greatest we could pull away from those two. And then let's go to the bottom. Now notice, this 6 doesn't have a p, so I can only talk about numbers here, but what's the greatest common factor between 2 and 6? 2. And then we'll go vertically. So on the left, I've got p to the 6th and p to the 3rd. So that would be a p to the 3rd. And then over here, 3p to the 3rd and 6 means we can only pull out a number. And the best part about the box method is if you just do a quick check, you know if you're right or not. Let's look. P to the 3rd times p to the 3rd. Does that give me p to the 6th? 2 times p to the 3rd. That gives me 2p to the 3rd. P to the 3rd times 3. That works. And then the last box should always work. We get 6. So, my final answer is we're going to take the original 2p squared that we had from the start. That made our lives a little easier. And then we're going to do p to the 3rd plus 3 times p to the 3rd plus 2. And because they're both addition, and the fact that it's a cube, I know right away I'm completely factored right there as far as we can go. It's intimidating. I'll be flat out honest. This is not easy stuff right away, but the more you do it, you start making those conceptual connections, and that makes your life a little easier. All right, I'm going to get you started on this one, and then I'll have you try it on your own. What I feel, or what I've noticed in the years of teaching, is it's always the starting piece. Like a lot of students struggle with a problem like this. How do I start? Well, think of method 1. Can you pull out a greatest common factor from all of the terms to make your life a little easier? What is the largest common term that goes into all 3 of those? 4 and x squared. Notice that x squared. That's really important. So if you can pull out a 4x squared, what's left over is an x to the 4th, a negative 5x squared, and a plus 6. So now, I want you to look at what's left over in the parentheses, and can you break down that, kind of like we just did with the box and the circle in part B. We'll see how far you can go. let's take a look here. So I want to look at now what's left over once I pull out the 4x squared, and we want to always ask ourselves, can we factor? Sometimes it doesn't work, and that's fine. If it doesn't work, then that would be our answer, and that's as far as we can go. However, this one does work. And I'll admit that once you become really good at this, you could do this factoring in your head, and maybe you already got it. So what do? We multiply the corners, and I'm looking for factors of positive 6 that add up to give me negative 5. Negative 2 and negative 3. But then x to the 4th would be split up as an x squared and an x squared. And then if I factor across the top, each top piece has an x squared in common. On the bottom, it can only be a number because of the 6 here, so I can only pull out a negative 2. Going vertically up and down, they both have x's, so I can pull out at least an x squared. And then on the right side, it has to be just a number at negative 3. And again, you should be able to check your answers to see if everything works out in the box. It does. So my final answer, and usually what happens is kids will do this. And like, there we go, that's my final answer. Why is that not right? We took out that 4x, right? That 4x is still part of the problem. It didn't disappear. So it's still part of the piece. Now, Noah, you made a great comment there. Well, what about the negative? Can't that be broken down further? The answer is no on this piece, and the reason why, can you think of factors of negative 2 that add up to 0? No. Also, here's a hint, negative 2, or the number 2, is not a perfect square. And that's the key. Same thing with 3. Those are not perfect squares, so it can't be broken down further. If it was a 4, if one of them was a 4 or a 9 or a 25, a 16, 81, then we could. And again, you'll start recognizing those patterns as we do this more and more. Okay. Don't write this. As we hinted, there are special patterns, right? You don't have to memorize them. And we actually did the reverse of this yesterday. Yesterday, or the day before, we said, what if I gave you a plus b times a minus b, and we FOILed it out, and we got that answer? Well, today, we're undoing that, right? If you see a squared plus b squared, or a squared minus b squared, then it can be factored. So you can reverse those patterns that you may have noticed from the day before. Same thing with the trinomial. Remember the a plus b squared? And we FOILed that all out, and it gave us this nice fancy expression. Or if it was a minus b squared, it gave us this. If you recognize those, then you can quickly save some time. Here's what I mean. What if I gave you this one? And again, I don't think you need to write it. This is a special pattern. And the reason why, what kind of number is 49? Perfect square, right? So, without doing much work, I would have to get a 7 here and a 7 here. However, if I was to FOIL this out, or the middle term is negative 2a times b, well, negative 2 means there would have to be a 7 here and an x here, which just tells me they would both have to be negatives. Again, if you see this, cool. If not, you know the box with the circle in it, and that will get you where you need to go. Okay? I do want to point out that this answer is correct, but there's a better way to write it. X minus 7 times itself is better written as x minus 7 squared. And that'll come up. So if you see that, just know you can factor that or write it as a better expression. Okay, let's look at method 3. This is tricky. And definitely write these patterns down. This is the only pattern that I'm going to have you focus on, because there isn't a great way other than this pattern to do what we call the sum or the difference of cubes. And actually, I'll just have you guys write that, and then we will explain it. So right now it means probably nothing with this piece right here. So now here's the thing. This looks like it's kind of friendly. Oh, x to the third minus 27. That's not that crazy of an expression. However, we want to look at the idea that these are cubes. Now, notice how this is a minus. So we're going to focus on the difference of cubes here because it's a subtraction. And remember what the word cube means. Cube means to the third power. Well, I have x to the third power, which is the same thing as where the a is. But I don't have a b value to the third power. But I do have 27. 27 is a very special number. What's a better way that we could write 27 right now?
9 to the third power.
Close. 3 to the third power, right? 3 times 3 times 3 is 27. And that's the thing that you have to be aware of. So we're going to first rewrite this. And we're not changing the meaning, we're changing the appearance. Okay. So, what does that tell me? That tells me that I'm in this exact same form as the pattern for the difference of cubes. So what I like to do, and I don't know if you want to do this, but just so you guys can see vertically kind of how everything perfectly aligns, you will not be expected to memorize this, by the way. It's just, you need to have it in your notes so you can access it. So what is it? If I want to take x minus 3, that's the a and the b, all I'm going to do is plug in wherever there's an a, I'm going to plug in x. And then we're going to, all the signs follow as is. So this isn't a negative 3, we're just, b is 3 here. So I'm going to have x minus 3. And then I've got a squared. Well, what is a squared? A is x, so this will be x squared plus, now, a times b, well, a is the x, b is 3, so a times b would be 3x. And what do you think the last value is going to be?
9.
9, right? B is 3, and then it says squared. So you could write it like this. You could write 3 squared, but instead of 3 squared, we're going to call that 9. And here's the best thing about these patterns. You're done. And that's it. It's not bad. That is a completely factored form of the x to the third minus 27. Okay. Now, it's tricky because some students aren't really strong with the idea of cube numbers. And if that's the case, you could do this just to help yourself out. And we're not going to go crazy with cube numbers, by the way, because they grow pretty quickly, but 2 cubed is 8. You know, 3 cubed is 27. 4 cubed, well, 4 times 4 is 16. 16 times 4 is 64. 5 cubed, 5 times 5 is 25. 25 times 5 is 125. And then I start losing track, and I grab a calculator. So, and you don't have to have these memorized, right? You can just do 6 times 6 times 6 or 216. But to be honest, a lot of the ones we see come from the first couple of values. Right? They don't, if they get higher, then you can kind of just check. But this list does keep on going forever. Okay, so let's look at this last one. This is a little bit tricky because it's got more than just numbers going on. Now notice this is a difference, right? Because it's subtraction, so we have to use the difference of cubes. But what I want to do, I need to rewrite this so it's in the form of a cubed to b cubed. And some students like to put parentheses around that because the whole thing has to be cubed. So this is friendly right here. I would write this down too, by the way. I'll give you a second to write that down. This did come right from Delta Math, so you know you'll see something similar to it. I'm going to steal this right from above. That's the difference of cubes. So that's the pattern we have to find, right? So my question then is, how can I rewrite this so I know what a and b are? Well, h to the third is fine. Maybe I want to think of it like that, but there's my a value. Right? That one's not super tricky, but then I have the subtraction of 64. What's a better way to write 64? We can rewrite 64 as 4 to the third. And then notice how this has a w to the third? Officially, that's how it looks right now. But if 4 to the third power is times w to the third, aren't they both being raised to the same third power? We're going to rewrite this as 4w to the third. So, what's the a value now? H. So, basically, wherever you see an a, you're going to write an h. What's the b value? Or w, right? So it's more than just a single number, it's a monomial term. And that's what we're going to do, is we're going to take that pattern and just plug in wherever you see an a, we'll put h. Wherever you see a b, we're going to replace it with 4w. And then when we do h squared, now what do you think a times b is going to give us? 4wh. And I think it doesn't matter how you write it, to be honest, but I think they're going to have it alphabetical. So numbers first, and then h, and then w. And then this is really the only spot that I see kids make an error. What do you think b squared is?
4w squared.
Very close. If we think of it as 4w squared in parentheses,
16w squared.
16, right? And that's the part that really, it's the only part that I really see a lot of errors, is the 16 is you're squaring both the number and the numerator, or the variable. And there you go. And again, because we use the pattern, that's as far as we can take it. We know for sure that it's completely factored. Okay. The last method looks intimidating because there's more terms. It's actually one of my favorites. It's called grouping. there's a hint when to use this. Okay. My hint is anytime you have a four-termed polynomial. So if there's four terms, we're going to group the first two together and group the second two. Okay, so that's why we call it grouping. And when we say group, we'll group the first two, and then we're going to group the last. So now notice, we couldn't do this if I had less than four terms, if I had more than four terms. So it only works when you have four terms. And then we're going to just pull out a common term between each factor. So for this first group, what do these two have in common? Squared, right? We're taking the largest possible, and that's key. You do have to take the largest. And then what's left over? And if you are somebody who has to do different colors, this would be a perfect color scheme to do here. So I have an x plus a 7 left over. All right. Now we're going to go to the next group. And what is the largest factor that goes into both negative 9x and negative 63? And let's pull the negative here. And I'll give you a hint. Oops, I want that to be in black. I'll tell you why I want the negative. Okay. What we want then is you want the remaining group to look exactly like the first group. So I'll have an x plus 7 left over. Okay. Now here's the tricky part. Okay. When you look at this, you have a multiplication minus a multiplication. Some students like to think of this as like a left side and a right side. What does the left side have in common with the right side? X plus 7, right? So now we're going to factor out, because it's common, the x plus 7. Okay. Now, it won't always be an x plus 7, but we're going to factor that out. So I'm going to pull it out from this one, and I'm going to pull it out from this one, so I'll only have 1. And what's left over is the x squared and the minus 9. Every year, students really struggle with going from this step to this step. And the question I always have to answer is, how come there's only 1? We had 2 x plus 7s, but why did I only write 1? Because we're factoring it out. So, don't write this piece, but I'm hoping it helps. I'm going to erase it. What if I undid the step I just did? What if I took x plus 7 and I distributed it to x squared? Wouldn't I get this part right here? And then what if I took x plus 7 and times it by negative 9? Wouldn't I get this part right here? So that's why we only write it once, because we're undoing the distributive problem. And that's the number one question I answer. The kids always ask on that. But that looks confusing. So we're almost done. You want to look at this, and we factored it here. X plus 7 can't be broken down. Well, what do you notice here? perfect square and the minus. So we're going to rewrite this as, what's a better way to write x squared minus 9? X minus 3 and? Look at you guys are already seeing these patterns. And now we are completely factored. Whew. That's a lot, right? We'll get there. I just want to show you one more grouping, just so you guys can see it. You don't have to write it down. I think it's just good to see it again. And I always plan too much, so we are definitely not doing these. But let's look at this one. Okay. How do you know right away that I have to use grouping? Right? And this is just the number 3, so don't worry about that. So what are we going to do? Let's group the first 2. I want this color. Group the last 2. Notice how I included the negative in this, so that's negative 16. And I'm going to pull out. What do these two have in common? The largest term that these two share is an x squared. And what's left over is x minus 3. And now here's a hint. If factor by grouping is going to work, I have to have an x minus 3 left over here. So I'm going to pull out what goes into these two. Well, if I'm going to have an x left over, I have to try to pull out the 16. But I also want that negative to come out. So if I pull out a negative 16, x is left over. And what if I take a negative 16 factor away from 48? You know it's going to be a negative 3. You see that common factor on the left side and right side now? And again, you don't have to do this, but some students like to think of this as a left side, right side. The left side and the right side both have an x minus 3. And what's left over is x squared minus 16. And then I'm not done because x squared minus 16, that 16 is the perfect square with the minus. If it was a plus, we couldn't break it down. But it's a minus, so we can. There we go. I feel like we just ran a marathon. We did. But you guys are math elites. You're in perfect form. So, here's what we got. Tonight, the homework is Delta Math, and it's just working on factoring. Quiz on Friday. It'll be on Schoology. It's like 5 or 6 questions, and it's going to be based off of what we did this week. So, factoring and adding, subtracting, multiplying polynomials. All right. Adios to everybody on Zoom. Have a wonderful day.